E1 elimination, they happen simultaneously with SN1. It's a two-step reaction, and they do happen with weak bases. Now, weak bases are also weak in nucleophiles, and these are all the neutral ones except the sulfur now. So all oxygen and nitrogen bases, these are neutral bases, and those bases, they favor E1 and SN1. I'm going to go ahead and add ammonia as well, because these are the derivatives of ammonia, both of them. So ammonia as well is considered to be a weak nucleophile and a weak base. Whenever you see it, then the reaction is going to proceed by both SN1 and E1. As we did for SN1, the rate of the reaction depends on the first step, which is the step that you form the intermediate. So this is why it depends on the concentration of the alkyl halide. The first step is a very slow step, and this is the step that we use to determine the rate of the reaction. The reaction is going to have an intermediate, and the intermediate is going to be a carbocation. So please rearrange every time you have a carbocation. And rearrangement happens by either moving a hydrogen or moving a CH3, as we've talked earlier. Rearrangement happens from a secondary to a tertiary only. So if you have a primary carbocation, you cannot rearrange to a tertiary or a secondary, because primary carbocations, they do not exist. As for the type of the alkyl halide that you are going to start with, like E2, we're going to start with the same type of alkyl halide. We're going to start with a tertiary alkyl halide. So you're going to notice here that E2 and E1, both they favor the most substituted alkyl halide to start with. So with E1, you start with alkyl halide or a secondary, and that's it. There is no way that the reaction is going to carry with primary alkyl halide for E1 and SN1, because primary alkyl halides cannot form primary carbocations. After all, remember that the first step of the reaction is the bromine leaving. This is the first step of the reaction to make the carbocation. So if your carbocation is not stable, if it is not a tertiary or a secondary, then it will not form. And the primary carbocations, they don't form. SN1 is always going to happen with E1 because the weak nucleophile also acts as a weak base. So the first step is always common between SN1 and E1, where the bromine is going to leave. This is going to be the first step. Now, when the bromine leaves, you're going to create a carbocation. Always ask yourself, can I make it more stable? This one is a tertiary carbocation on its own, so you cannot stabilize it further. But if it was a secondary, you have to move an adjacent hydrogen or an adjacent CH3. Now you have to consider the cases where the nucleophile acts as a weak base or the nucleophile acts as a weak nucleophile. So if it's acting as a base now, the base always takes the beta hydrogen. So figure out how many different types of beta hydrogens. All these are going to be beta hydrogens because they are one type. They are all CH3s lying in there. After all, the alpha carbon is the carbon that is connected to the halogen. If the halogen leaves, then the alpha carbon is going to be the one that has the halogen on it. And if you do rearrangement, then the alpha carbon is going to be the one that carries the plus charge. So here, this is going to be the alpha. Look at the adjacent. You have betas, but all the betas are the same. So just pick one. No need to write repetitive products. So the base is going to come, take the beta hydrogen, form a double bond. There is no leaving the group here because the leaving group left in the first step. You're going to get your E1 product. Now, when the methanol acts as a nucleophile, you're going to get your SN1 product. Notice the difference in the role of the base and the nucleophile. Both are the same, but we know bases take beta hydrogens. Nucleophiles, they attack the sp3 hybrid carbon. So they do attack the sp3 hybrid carbon in there, and you're going to end up getting your product. Remember, in SN1, I always use the solvent as the deprotonation in the last step. And the solvent in this case is water. So I'm going to use water. I can use another methanol if I want. So either methanol or water, any base in the solution, can come and pick up this extra hydrogen, and you're going to end up getting your SN1 product. Now, SN1 product proceeds by inversion and retention and configuration, but because this carbocation has three groups that are the same on it, it is not a potential chiral center. So this is why I ignore stereochemistry. But if it was a potential chiral center, where when I add the fourth group, it will be a chiral center, then I would need to consider the nucleophile attacking from the top and from the bottom, because it is a planar carbocation, and we're going to get two products, and these products are going to be a racemic mixture. Let's have this example. A secondary alkyl halide with a CH3 over here, and we are reacting this with ammonia. Okay, now in this case, I know that ammonia is both, it is a weak nucleophile and a weak base. So this reaction is going to proceed by SN1 and E1. Again, notice that similar types, they happen together. So you cannot confuse the one with the two. You cannot mix them together. So you cannot say that the reaction goes with SN1 mechanism and with E2 mechanism, because SN1 and E1, they are both carried by the same intermediate, which is the carbocation. SN2 and E2, they don't have an intermediate. They are one-step reaction. So the first step, we're going to create the carbocation. And to create the carbocation, the bromine is going to leave, and you're going to form the carbocation. Now, the carbocation is going to be common between both the SN1 and the E1. So you're forming a carbocation here. Now, you can rearrange by moving the CH3, because you want your positive charge to be on the most substituted carbon, to be major. Right now, my carbocation is a secondary carbocation, and I can easily move it and make it a tertiary, or rearrange it and make it a tertiary carbocation by moving a CH3 to the carbocation. The reason I'm moving a CH3, because on this hydrogen, on this carbon, I do not have a hydrogen. So this is why I'm allowed to move a CH3. But if I had the hydrogen on this carbon, you move the hydrogen, you don't move the CH3. So you do the rearrangement, and you're going to end up getting the carbocation here. We still have a CH3 there, and we did a CH3 over here. This is what we moved. So that is going to be the tertiary carbocation in this case. Now, once you form the carbocation, I have two routes to go with. I can use the ammonia as a nucleophile. Now, this is NH3 as a nucleophile, or I can use it as a base. Let's consider the ammonia as a weak nucleophile. So that is going to get me my SN1 products in there. Now, since this guy is a planar carbocation, and it has three different groups around it, and if I add the ammonia, it will be a four different groups, so I'm creating a chiral center. So I'm going to go ahead and consider the stereochemistry by showing that the NH3 is going to attack on both sides of the carbocation, in front and the back. So you're going to end up getting, here you go, this is the two CH3s, and the NH3, all the NH3, you guys. So all of the NH3 is going to attack the nitrogen and the three hydrogens, and you are making a bond between the nitrogen and the carbon in there, plus the NH3 can attack at the back. Okay, of course, if the NH3 attacks at the back, this guy is going to be in front, and if it attacks in front, this one is going to be at the back. So you can show stereochemistry. Now, in this case, I am creating a chiral center here. Nitrogen is a plus a charge. I cannot have a charged product. My product need always to be a neutral. So in this case, I'm going to use a solvent. Since in my reaction, I did not say that I'm using a solvent here, just a nucleophile, then I'm going to consider that nucleophile a solvent as well. So after all, this one is a base, and I need a base in order to come and pull the extra hydrogen and form a neutral product. So I'm going to use it as a base over here. And I'm going to end up having my two SN1 products, and these are going to be a racemic mixture in there. So I'm going to have the NH2 here, plus I'm going to have the second product there. These two are optically inactive because they come from an optically inactive reactant, which is the carbocation in there. So these two are racemic mixture. It's both inversion and retention in configuration, 50% R, 50% S. We have here two chiral centers, so if we want to figure out the configuration of each, this is going to be priority 1, this is going to be priority 2, priority 3, and the priority 4. So you can go ahead and switch the 2 with the 4. So you're going to end up getting the 2 to be in plane, the 4 to be behind, which what we need, and then priority 1, which is in front, and then priority 3, which is in plane. And going by 1, 2, and 3 like this is an R configuration, so this chiral center is going to be an S. Let's do the second one. This is priority number 1, this is 2, this is 3, and this is 4. We can go ahead and switch 1 with 4 and make now 1 to be in plane. Let's put the 1 in plane. So we're making 1 in plane, and then we're making 4 behind, and then 2 is going to be in front, and then 3 is going to be in plane. And here in this case, we are going by 1, 2, 3 like this. This is an S configuration, so its actual configuration is going to be an R. So you can notice that here I have 50% R, so 50% R, and 50% S. So if I combine those two together, I'm going to end up getting an optically inactive SN1 product. Let's have another example. I'm going to use the OTS. It's a better leaving group than the halogen, and we are using still a weak nucleophile and a weak base. If we specify that we're using heat, then E1 is going to be the major, and you don't even have to mention the SN2, the SN1. If we specify that we are using heat, then E1 is going to be the major product. You don't even have to mention the SN1. However, if we don't use heat, so if there's no heat, you can go ahead and write down both the SN1 and the E1 products, both of them. So these two with no heat. Okay, let's go ahead and assume that there is no heat and do the mechanism. So the first step, the OTS is going to leave, and you are going to end up getting your carbocation in this case. Carbocation is common between SN1 and E1. So you're going to end up getting a carbocation. Whenever you form a carbocation, you don't need to show any stereochemistry now for the CH3. See, the CH3 was in front, but when the OTS left, now everything became in plane. So all of those are planar. This is an sp2 hybridization, and it's planar in this case. So do not show any stereochemistry because it's not a chiral center after all. Now I do have two CH3s in here. This is a tertiary carbocation, And you guys, if we move the CH3, we're still going to get a tertiary carbocation, and it's going to be exactly the same as this one. So no need for us to move any CH3 in there. It's a stable carbocation. So now after you do this, you have two routes to go with. The methanol can act as a base or as a nucleophile. So if it acts as a base, then in this case, I need to locate my alpha carbon and my beta hydrogens. There is no stereochemistry like E2 in this case. So the beta hydrogen here can be anywhere. It doesn't have to be anti-periplanar because we already lost the halogen. So there is nothing for to repel in this case, the base. So the base can come from any side in there. So this is going to be my first beta hydrogen. I'm going to label it beta 1. This here is going to be my second beta hydrogen. This is beta 2. And on this carbon here, there is no beta hydrogen. So there will be no elimination. So I'm going to end up getting two products. The double bond can either be here or it can be here. So now the base is going to come, take this beta hydrogen and form the alkene. And you're going to end up getting the double bond. Plus, the base is going to end up attacking the beta 1 hydrogen and forming the alkene on this side, and always the alkene is formed between the alpha and the beta carbons. So if you see over here, my alkenes are two types of substitutions. They are tri-substituted alkene, and it's a tri-substituted because the alkene is connected to 3 carbons, versus here a disubstituted alkene. Now this disubstituted alkene does not have cis and trans because the double bond has two groups that are the same on this end. So this disubstituted alkene is just a disubstituted alkene. No cis and trans isomers here. So this one is a major, to be the major Zaitsev E1 product. As we did for the SN1, if you have, or as we did for the E2, if you have more than elimination product, you can always write the major one and forget about the others. We can also use the methanol as a nucleophile. And if this is the case, check if you have a potential chiral center, then the nucleophile is going to attack from both ends of the carbocation. So yes, here I do have 3 different groups around the carbocation. So I have a potential chiral center. So the nucleophile is going to come and attack. Let's use a different color. So the nucleophile is going to come and attack either from this side or it's going to attack from the opposite side. So you're going to end up getting 2 products in this case. And they're going to be a racemic mixture. So always with SN1 reaction, you are going to get a racemic mixture. So I'm going to end up forming my methanol to be either in front. And notice how am I drawing the oxygen connected to the carbon? This is going to push the CH3 to be at the back. And it's going to make it chiral because of the 2 CH3s here that makes this side different than this side. So this is a chiral center. So this is my chiral center in there, plus my second isomer, where my CH3 is going to be in front, and the methanol is going to attack from the back. And then I have my 2 hydrogens in there. And again, this is a chiral center. As we keep saying, since I don't have a solvent, I'm going to use this again as a solvent with SN1 reaction. So I'm going to use it now as a base. And the base is going to come and take the acidic hydrogen, the extra hydrogen, to give me my neutral product. So I'm going to end up getting 2 products in this case, and those products are going to be a racemic mixture with respect to each other. If I combine them together, because one is 50% R and the second one is 50% S. So these two, combining those together, they will be optically inactive because they are a racemic mixture. Now, if you have a primary alkyl halide, of course, with any type of weak nucleophile, weak base, let's say, for example, water, then there will be no SN1 and there will be no E1. There are additional examples in the notes, so please go over these examples and practice the mechanism of the reaction.